Well, our next speaker this morning is Rolf Silva, and he is going to talk on entanglement enhances performance in microscopic.
Right. So, as was mentioned, I will be talking about the role of entanglement in quantum thermal machines with specific focus on a particular model. And at the outset, let me state that this work is collaborative work with Nicola Brunner, Markus Huber, Noah Linden, Sandu Popescu, and Paul Skripczyk. And although they are at the moment in various places in the world, at some point or the other when this research was done, they were all at the University of Bristol. So before I begin, just a little bit on thermodynamics itself. Sorry. So the reason that quantum thermodynamics is becoming more important is, of course, because machinery and processes that we study are getting closer and closer to the quantum scale as ever. And we can imagine that as a machine reaches down to the size where the number of quantum states actually involved in the machine is countable, say about 10 or 20 rather than a classical machine where there are 10 raised to 20 or more, you can imagine that quantum effects will start playing. Sorry?
You're using countable in a way that is
Oh, sorry.
inimical to a mathematics exam.
Sorry, I don't mean countable. I mean the sort that you can count on the fingers of your hand, but not including countably infinite. So sorry. Yeah. So these quantum effects become more and more important. And when we actually study quantum thermodynamics, there are two directions in which this study can go. So the first is a theoretical study of how quantum the laws of thermodynamics, which are quite well understood on the classical scale, reflect on the quantum scale. So for example, we study the second law, whether the second law is valid on the quantum scale as well. And we study various quantum cycles in order to study the concepts of efficiency and things like that. And recently, we have a greater interest in the concept of a self-contained quantum machine, because there are many quantum processes that are done with a large input of external energy. For example, we know, I will be talking about a quantum refrigerator, but we know that we can achieve cooling with lasers, for example. But in that case, the amount of energy that is being inputted is either unaccounted for or is much larger than the energy of the quantum system. So what we would prefer is to study a self-contained quantum system, one where all of the energy and inputs and outputs are accounted for within the quantum system itself. And the interesting questions we can ask about such machines is, first of all, does the fact that the size is finite and in fact small in the number of quantum states pose an extra constraint on the machine? So we can imagine that classical machines have their properties because we take them in the asymptotic limit. So because the number of particles can be treated to be tending to infinite, we have all of these quantities such as efficiency. But it may be that the finite number, the small number of states, leads to extra constraints in the case of quantum machines. The other question is the converse, of course. Does the fact that this is a quantum machine and we have things like superpositions, coherence, and entanglement provide us with extra opportunities to do something that we could not do with classical machines? And this is, of course, the question which I will be focusing on the rest of the talk. And when we want to study the quantum nature of a thermal machine, we basically study its entanglement, because this we treat as the paradigm of quantum mechanics, what really distinguishes quantum mechanics from classical. So the particular model I will be studying is the simple quantum refrigerator, and schematically it's shown in this diagram. Essentially what we have is a single qubit that we require to be cooled. So this is denoted by E1 here, and it's connected to a thermal bath that is at a particular temperature labeled by the cold temperature. And our goal is essentially to cool this qubit to below the temperature of this bath. But in order to do so, we have access to two other thermal baths that are hotter than this cold temperature. So this is so that we cannot simply cool by connecting this one to a colder bath. We do not have access to a colder bath. We have access to two differing temperatures. And they're labeled T-hot and T-room, essentially. And the goal is to, using energy from the hot bath, to absorb energy from the cold bath and deliver it to the room bath. So essentially this is the working of the heat. We want to couple the energy flow from the hot and the cold to give it to the room bath. And in fact, even though this is essentially a 3-qubit machine, this schematic working of the heat flow is identical to classical thermal fridges. So you can actually commercially purchase a thermal fridge that will operate with 2 thermal baths and provide cooling. Right. So in this particular machine, each qubit, the connection between each qubit and its thermal bath is modeled by a Lindbladian dissipator. So this model essentially says that per unit time, there's a probability of the state of the qubit, whatever it may be, to be reset to the thermal state of the bath, which is given by, well, the standard Boltzmannian form of the thermal state. And so this is dissipation. The other thing that we do, and this is critical to the working of the fridge, is because we want to couple the energy flow from hot and cold to room, we design the energy levels of the hot and the room temperature qubits such that there is a degenerate subspace. So the difference between the room and the hot energy levels is given by the energy level of the cold qubit, and this results in the degenerate subspace 101 and 010, which essentially the going from this state to this state corresponds to taking energy from the hot and cold and delivering it to the room. And in order to do this, we engineer interaction Hamiltonian, which works in that degenerate subspace. So it is energy conserving. So the first thing to point out about this fridge is, as we aim to do, it is self-contained. So all of the energy and input is accounted for because we can calculate the energy input and output per unit time by using the dissipator. And the overhead, so you can imagine that to start this machine, you require a particular amount of energy, but because once you begin the working of the machine, it runs essentially for as long as you want, this initial energy, which we call the overhead, is insignificant at the asymptotic limit. So this machine is perfect to study the concepts of efficiency, for example. The other point to note about this model is it works in the assumptions that we've taken, the Lindbladian dissipator and the other assumptions work in a particular regime depending on the parameters of the fridge. So for example, because the temperature is defined in terms of the population of the 2 energy levels, we require that the energy levels should not change, and for that the unitary should be much weaker than the Hamiltonians of the qubits themselves. And we do have physical examples of such Lindblad dissipators for when the dissipator strengths are also much less than the energy levels. So if we increase Pi to be comparable to E, this will correspond to a theoretical model, but it's not very clear whether there's a physical system that would give you the same answer. So essentially how this machine works is it couples dissipation and coherence. The coherent interaction transfers energy from 2 qubits to another one, and then the dissipation essentially takes that energy into the bath. And this whole thing can be modeled by a single master equation, where the first part is essentially the Hamiltonian of the qubits and the interaction Hamiltonian, and the second part reflects the dissipative dynamics of the machine. So before the interaction Hamiltonian is turned on, so we have only dissipative dynamics, you can imagine that the steady state of the fridge will simply be the product of 3 thermal states because each of them are connected to a thermal bath. So before the Hamiltonian is turned on, the state is simply the product of 3 thermal states. After we switch on the Hamiltonian and we wait for a long time, a sufficient amount of time so that we reach the steady state, the steady state solution is given by a very simple form, which is essentially the initial state plus a parameter gamma, which is important, and I'll tell you why later, into 2 matrices of this form. And the properties of these matrices is essentially eta d is a diagonal matrix. So all it does is it shifts the diagonal values of this density matrix from their thermal values in such a way that when we take the reduced states of the qubit after we turn the fridge on, we find that each of them has changed in temperature slightly. So the cold one will be colder than its thermal bath as we require, the hot one as well, but the room one will have heated up. And the special properties of this Y is it's an off-diagonal matrix, and it has only 2 non-zero off-diagonal terms, which correspond essentially to the degenerate subspace that the interaction Hamiltonian worked on. So the density matrix of the fridge is very simple. It's an 8 by 8 density matrix because it's a 3-qubit density matrix. It has only diagonal terms except for 1 pair of off-diagonal terms, which are, of course, complex conjugates of each other. And when we want to study entanglement in tripartite systems, in general, this can be a very complicated affair. But because we have only 1 pair of non-zero off-diagonal elements, the entanglement witnesses for this class of states is actually quite simple. So for the entanglement witness, we choose a partition, which is denoted by S. So because this is a 3-party state, there are 3 ways of partitioning the system into 2 qubits and 1 qubit. And along that partition, we compare the non-zero off-diagonal element with this form of the pair of diagonal elements corresponding to that partition. So the first thing to consider is the Carnot point of the fridge. And by saying the Carnot point of the fridge, I say this because one of the fundamental results of this model is that the quantum bound on the efficiency is the same as the classical Carnot efficiency. So remember when I first talked about whether the size, the quantum nature poses an extra constraint on things like efficiency, and it turns out that this is not the case, that this particular quantum refrigerator can reach the same maximum efficiency that a classical Carnot machine could reach as well. So the efficiency, of course, is defined the usual way. We divide the power that we can absorb from the cold system upon the power that we have to input from the hot system. And in fact, from the steady state solution that is given above, we see actually that the efficiency, eta, approaches the Carnot efficiency as this parameter gamma, which I mentioned, tends to 0. So as this gamma tends to 0. And so now we are able to answer the first question about these machines. So does entanglement, so does quantum entanglement, enhance the efficiency of these machines? And the answer is trivially no. And this can be seen very simply because in the previous slide, when gamma tends to 0, which is when the efficiency tends to Carnot efficiency, the steady state essentially approaches the initial state, which is a product of 3 thermal qubits, and that's of course trivially separable. So we see that at the Carnot point, the steady state is completely separable, which means that there is no entanglement. And because this is a continuous relation between the parameter gamma and the Carnot efficiency, we can actually prove that at and around Carnot, so in a particular neighborhood around the Carnot point, the steady state is completely pi separable. Although this may seem like a shocking result at first, it's not as surprising as it seems, because even in the case of classical thermodynamics, we know that as we approach Carnot efficiency, we also approach reversibility, so that in fact at the Carnot point, the classical machine will be maximally efficient, but it will be completely reversible and therefore have 0 power. It won't actually do anything, which is the same thing that we see in these machines. At the Carnot point, it's simply the product of 3 thermal states, which means it's not doing anything, 0 power. Right. So next thing to ask about entanglement is to see whether away from the Carnot point, do we find entanglement in this fridge or not? And the answer is a firm yes. In fact, if we vary all the parameters of the fridge and we look over the entire space of steady state solutions, we find that we can find steady states exhibiting entanglement across any bipartition that we like. So there are 3 bipartitions, and we find it across any bipartition, and even simultaneously across all 3, which would mean that the state would be genuinely entangled. It would exhibit genuine tripartite entanglement. So this is an example of the concurrence across each bipartition. And you see that by varying the parameters, we can achieve entanglement witness violations across any combination of bipartitions we like. So once we know that we have entanglement in this fridge, the other thing to talk about, other than efficiency, is cooling power. So for any thermal machine, there are 2 parameters that determine its performance. One is the efficiency of the machine, but the other is just the absolute power of the machine. So in the case of a refrigerator, what you would like to ask is, how much can this refrigerator cool a system, or how much power it can absorb from a system which is supposed to be cool? So the cooling power essentially of the fridge. And so the question is, does entanglement enhance the cooling power of the fridge? And just to explain what we did to answer this question. So what we mean by this question essentially is that we are given a physical qubit to be cooled. So the energy of the cold qubit, the temperature of its bath, and the dissipative dynamics between the cold qubit and its bath is given to us, is fixed. And then we are allowed to optimize over the remaining parameters. So the energy levels of the other 2 qubits, the temperatures, the dissipators, as well as the unitary G, subject of course to the constraints of the model that I mentioned earlier. And we optimize over all these parameters to maximize the power, that is the amount of heat that is absorbed from the cold bath. And in this model, it turns out that maximizing the power and minimizing the temperature that cold bath reaches is exactly the same. And then we repeat this optimization, but then we demand that the steady state solution in the optimization is separable. So first we perform the optimization with no constraints on the density matrix, and then we perform it with the separability constraint. And if these 2 give us the same answer, it would mean that separable fridges do as well as entangled fridges. But if it is the case that the first optimization gives us a better power QC, then it would essentially mean that entangled fridges are somehow cooling better than separable fridges. And the result is that in fact it is the case that there are qubits physical qubits. So there are values of these parameters that for which, when we optimize over all of the fridges, we find that the fridge that achieves the most cooling is an entangled fridge, so it's an entangled state. So this is the first result that suggests that entanglement does play a role. But there is more to suggest the role of entanglement. And so the first thing we did once we found the fact that entanglement seems to enhance cooling, we studied what the relationship between entanglement and the amount of cooling enhancement is. So we define the cooling enhancement essentially by, you take the temperature difference that you can achieve with an entangled fridge, so the difference that it can, between the temperature it can reach and the temperature of the bath, and then you take the temperature difference that you can achieve with a separable fridge, and you simply take the ratio of these two. And this is a number that is greater or equal to 1. So that's a relative cooling enhancement. And then you take the concurrence across a particular bipartition. I will mention what this bipartition is in a minute. So the concurrence, of course, is the amount of the violation of the entanglement witness that we have for that bipartition. So it gives us essentially a measure of the amount of entanglement. And so what we did is we fixed most of the parameters, and then we varied only the temperature of the room temperature, so the temperature of the sink bath. And we found that as we varied that temperature, as the concurrence increased, which is along this axis, the cooling enhancement also increased monotonically. So essentially the cooling enhancement had a monotonic increase with the concurrence when we varied the room temperature. Now this suggests a functional relationship between the cooling enhancement and the concurrence. It doesn't simply seem to be a coincidence, but rather because they move monotonically, there may be a functional relationship between them. The other property of this entanglement that we found in the optimized fridges was that, so recall that I said we took the concurrence across a particular bipartition. And the reason we did that is because it so happens that when we optimize for the best possible entangled fridge, we find that the optimized fridges, they have entanglement solely across one particular bipartition. And this is the room versus the hot and cold bipartition. And this is significant because this partition corresponds to the energy in versus energy out, because we take energy from the cold and the hot baths and we dump it in the room bath. So the bipartition across which there is entanglement is solely this one. And this is significant because recall that we have steady states of the fridges without the optimization constraint. We found steady states of the fridges that exhibited any kind of entanglement that we required, so across any bipartition that we wanted. But it seems that among all of these entangled fridges, the ones with entanglement across this energy transport bipartition perform the best in terms of cooling power. And one example of an actual physical system this may possibly be relevant to is photosynthetic complexes. So in the case of light harvesting complexes in photosynthetic systems, these are essentially complexes that absorb a photon from the environment and then transfer the photon to a reaction center which uses up the photon. But the reaction center is very small, which means that the photon takes quite a bit of time to reach that reaction center. And it so happens that these complexes are extremely efficient at getting the photon once it's absorbed to that reaction center. And one of the mechanisms that has been proposed to explain this is quantum coherence. So it may be the case that the different components of this complex are actually coherent superpositions. If that is the case, then this result that entanglement enhances energy transpose across a bipartition would be relevant to such a system. So to summarize, we have that the refrigerator, when we study entanglement in this refrigerator, the fridge is separable at and around the Carnot point. So it is in a product state at the Carnot point, and it is separable in a neighborhood around the Carnot point. Away from the Carnot point, we find regions of entanglement, and we can find steady states that exhibit entanglement across any and all bipartitions that we require. There are qubits for which so if we choose a particular physical qubit, we can find cases for the cold qubit such that the optimal cooling power is achieved by an entangled state of the fridge. So the steady state solution that achieves the optimal cooling power is an entangled state. And this particular entanglement is related monotonically to the cooling enhancement. So as this amount of entanglement increases, we find that the cooling enhancement also increases. And the entanglement that enhances cooling, unlike the entanglement that we can see across all bipartitions, the one that enhances cooling is solely across a single bipartition, and this is the bipartition corresponding to energy transport from the hot and the cold baths to the room bath. Thank you.
Well, we have time for questions.
I'm probably going to fail, but I'm going to try to ask a Charlie Bennett style question. So, do you have any intuition based on this why classical refrigerators are less efficient than quantum refrigerators?
It's not very easy to say. So the problem is that we have a model of a quantum refrigerator, but the only way to directly compare it to a classical refrigerator would be to get a similar, so a 3-bit quantum refrigerator similarly. And it's very difficult to construct such a physical model. So it's not very clear what exactly it is that makes the quantum refrigerators better than the classical. But it is the case that entanglement plays a role, and we know that entanglement is something that differentiates between quantum and classical machines. But why exactly this is not very clear. So in this case of this quantum refrigerator, the working of the refrigerator is essentially to build up coherence in that degenerate subspace and then to dissipate it away. And this, of course, is something that classical mechanics cannot do. It can only perform straight dissipation rather than building up coherence. So this could be one possibility. Just the fact that we can have coherence in quantum machines may be better than the classical case.
Let me add a comment to that. Many years ago, Scully's group came out with an idea that how atomic coherence could make the refrigerators or the heat engines work better than the Carnot engines. And again, the atomic coherence plays a very dominant role. And he had certain models in terms of three-level systems where you can easily build up coherence by external means. Okay.
I will try to ask a Rod van Metter style question. Or continue actually with his question. The question that I had in mind was that when you say impose the stochastic classical transitions with variable rates that you could adjust to optimize. Yes. Now, if that's the same thing, then I would say that was a reasonable classical analog.
Yes.
Of course, a real classical fridge has many more states, and it's hard to say which classical fridge is comparable to which quantum fridge. But I didn't quite understand your mathematics enough to say, is your constraint of classicality equivalent to making a classical model of a fridge that had a limited number of classical states?
No. So actually speaking, so when they derived this quantum model, Noah Linden, Sandy Popescu, and Paul, they actually tried to get, as you said, to try and derive a classical stochastic model that would reproduce this. And the thing is, they managed to get a classical stochastic model with just 3 bits and the stochastic transitions, which reproduced almost all of the results of the fridge in terms of heat flow and stuff like that. But they were unable to find an actual physical Hamiltonian, so classical Hamiltonian, that would give rise to such stochastic dynamics. So it was possible to make such a stochastic model, but it was not possible to find a classical Hamiltonian that would give rise to such a stochastic model. So,
if you said you didn't care about that, how would that efficiency of that model compare with the quantum model? If I just said, I will assume that if you might say implicitly there's some other bath involved, but any classical stochastic process I can implement with...
Well, if I didn't care about the Hamiltonian, it would diminish the results, because I think it was the case that this stochastic model that they had was, if they chose the parameters of the model carefully, they were able to reproduce the fridge exactly. So in terms of the heat flow, they exactly reproduced the parameters of the fridge, so the working of the fridge.
But the model was not so unphysical as to be able to violate the second law or anything.
No, it did not violate the second law, no.
Well, let me ask you a quick question.
Yes.
That interaction Hamiltonian that you used,
yes,
so that you can realize in many different systems?
There have been suggestions to use it in ion traps, essentially, because you can connect 3 ions and engineer a variety of Hamiltonians between them. So this is one of the suggestions.
Okay. Yes.
Just one question. The features that you've listed here,
Yes.
admittedly you have looked at the simplest possible refrigerator that one could have,
Yes.
employing simplest possible quantum systems.
Yes.
What features would go through if I were to replace this by, say for example, harmonic oscillators all along? Harmonic oscillator bath, the system,
Yes.
what difference will this, what features will go through in your opinion?
So this is the question that we look to answer now. I know that once you increase the number of energy levels, essentially each degenerate subspace plays the role of a machine. Essentially, once you have a degenerate, it's the case that all of the degenerate subspaces are the same type, which means that the sort of virtual temperature formed by the degenerate subspace is the same. Then the fact that the machine can reach Carnot efficiency will still remain true. If it's the case that the degenerate subspaces seem to be at different temperatures in terms of the working of the machine, then Carnot efficiency will become impossible to reach. The question of entanglement is far more complicated, and we are not sure whether this is. It actually is not even clear to us whether the working of the machine would be improved by adding more systems or not. Because in classical machines, you usually have the case that if you have two machines that are cooling a particular system, at the same time, the working would improve. But because this model relies on the creation of coherence, you could imagine that if you connected two different sets of hot and room temperature qubits to it, the amount of coherence between each of them would fall, and the machine would actually not work better. So it is not clear because of that what features go. But it's definitely the case that the Carnot efficiency relies on that thing, yes. Actually, I would also mention, just as a side note, that there is in the Feynman lectures on physics, he has this, the ratchet and Paul, which he uses to explain the second laws of thermodynamics. And that ratchet and Paul, when reduced to its simplest model, is actually is similar to a 3-qubit machine, where you have a hot bath, a cold bath, which is your spring, and the weight which you do work on. So the working is very similar. So.
Okay, let's thank our speaker.